Well, good morning. This is a lecture on Hurwitz stability. Now, let's just consider what we're looking at. We have a closed loop control system with a transfer function, GS, and a simple proportional controller here. And what we're looking at is we're looking at adjusting the gain and finding out at what values of gain the system can go unstable. And this gives us our Hurwitz stability concept. So we have the concept of PS plus KPZS equals 0, which we can convert into a polynomial in the form of a0 s to the n is a1 s to the n minus 1 plus a2 s to the n minus 2 all the way down to an equals 0. And it is this equation here that we put into the Hurwitz stability test. So the Hurwitz stability test now is in two parts. Part 1. This is quite simple. All the coefficients AI have to be positive. That means all these coefficients here have to be positive for the system to be stable. Then, having done that one, we can move on to part 2. And this involves forming what's called the Hurwitz determinant. And this is relatively straightforward to do. And the technique is as follows. We have a matrix, and the size of the matrix is n. So it's an n by n matrix, and let's form a little n by n matrix here. This is n this way and n this way. And with the Hurwitz stability test, what we do is we put in the odd coefficients along the first line. So that's going to be a1, a3, a5, and then we put in the even coefficients. It's going to be a0, a2, a4. And then what we do is we put in a couple of zeros here, and we copy these parts here into here to give us a1, a3, a5, a0, a2, a4. And we keep on doing this, putting an extra couple of zeros in here, a couple of zeros in there, and copying this bit into here until we get up to n. And then we've got the Hurwitz matrix. Now, the next stage with the Hurwitz matrix is we form subdeterminants. And these subdeterminants we form from the top left-hand corner. So we form one there, one there, one there, like that. And these now have names associated with them. So the first one's delta 1, the second one's delta 2, the third one's delta 3. So for example, delta 1 is given by A1, delta 2 is A1, A3, A0, A2, and delta 3 would be A1, A3, A5, A0, A2, A4, 0, A1, A3. Now, within these subdeterminants for stability, all the subdeterminants have to be greater than 0 as well for the system to be stable. So this has to be greater than 0, this has to be greater than 0, and that has to be greater than 0. Now, when Hurwitz came up with his stability concept, some other chap called Routh came along a few years later, and he had a simplification of this method. He didn't need to work out all of these. He could just work out either all the odd ones, that's all the odd coefficients, or all the even ones as a simpler test. So then we got all odd delta I is greater than 0, or all even delta I is greater than 0. And this then gives us our complete Hurwitz stability test. First of all the coefficients of the polynomial have to be greater than 0. Secondly, we form the Hurwitz determinant. We then get the subdeterminants, and we can either have all the odd ones greater than 0, or all the even ones greater than 0. And that then forms the basis of our Hurwitz stability test. Good afternoon. We're just about to do our first example on stability. Let's consider the following example. Here we've got a controller, and here we've got a transfer function. Let's make it 6 over s plus 1, s plus 2, s plus 3. And our job is to find out the value of the gain, Kp, at which the system goes unstable. So the first thing we do, put some labels on it. Call that V, call that Y. And that signal there is V minus Y, that signal there is Kp V minus Y. That's coming from this is that times that. Then we can say that this is that times that to get our equation for the closed loop system. To get that Y equals 6 Kp V minus Y over s plus 1, s plus 2, s plus 3. That's saying that this is that times that. We then can move this term here up here. So we get s plus 1, s plus 2, s plus 3 times y is 6 kpv minus 6 kpy. Now the next job is to multiply this by this by this. So let's look at that. So we've got s plus 1 times s plus 2 is s squared plus 3s plus 2. Then we multiply by the s plus 3. That's going to give us s cubed plus 6s squared, 11s plus 6. So that times that times that comes as that. So we can replace this now with this to give us that s cubed plus 6s squared plus 11s plus 6 times y equals 6 kpv minus 6 kpy. Right, so our next thing is to move this term here onto this side. Remember now, as it jumps over here, changes sign. So this equation becomes s cubed plus 6s squared 11s plus 6 plus 6kp times y equals 6 kpv. Now, this is the equation now that we're going to put into the Hurwitz stability test. So this first coefficient is A0, this one is A1, this one is A2, and that term there is A3. So the next thing we'll have to do is now to put these parameters into the Hurwitz stability test. So in order to do that, we'll have to clean the board slightly. So here we have now the equation, and we know now that the first part, Hurwitz stability test in two parts. Part 1, all the coefficients AI greater than 0. So looking at this, 1 greater than 0, 6 greater than 0, 11 greater than 0, 6 plus 6 kp, as long as kp is positive, that'll be greater than 0. So in this particular part 1 is passed. So we can then go on to part 2 now. And for this we have to form the Hurwitz matrix, and because it's a third order system, the matrix is going to be a 3 by 3. So we've got a 3 by 3 matrix here. And with the Hurwitz stability test, we put the odd coefficients in first. That's A1 and A3. So A1 is going to be 6, and A3 is 6 plus 6 kp, and there's no A5. Then we put in the even coefficients, which will be 1 and 11 and 0. Then we put a naught in here, and we copy this part here into here. That gives us 6 plus 6 kp. Now, we can now work out the subdeterminants. So this one here is delta 1. So delta 1 equals 6. Delta 2 we get from here. So delta 2 is given by 6 plus 6 kp, 111. And delta 3 would be the whole thing there. So we could have delta 3 as well. Now, in this particular case, we don't need to work out all of them. We can either go for the odd ones or the even ones. So the obvious one to go for is this one. So we want this one to be greater than 0. So in order to do this one now, it is a 2 by 2 determinant. So 6 11s are 66 minus 6 minus 6 kp greater than 0. So 6 minus 66 is 60. So 60 has to be greater than 6 kp, or kp has to be less than 10. So in our original system, if kp was less than 10, the system would have been stable. If kp is equal to 10, marginally stable. Kp bigger than 10, unstable. That's our first little example.